Hello, chemists. This is Ms. Placino, and you are watching Screencast 11.2 on rate laws. Today, we're going to talk about what rate laws are and what information they're able to provide. This is kind of an advanced lesson. When you get down to it, the math behind it isn't too challenging. It's a lot of hopefully straightforward algebra. Do make sure you have a calculator with you for this lesson. But kind of the thought process behind it can be a little bit challenging. In so many ways, this is more like a puzzle than it is actual chemistry, and it can be kind of fun to figure these out. So let's go ahead and get into the lesson. All right, a rate law is going to describe how the rate of a reaction varies with concentrations of reactants. So in the previous lesson, we talked about different factors that can affect rate, such as temperature, pressure for working with gases, surface area for working with solids, concentration, nature of reactants, and catalyst. And when we go to discuss rate laws, we are looking only at varying the concentration. We're going to keep everything else the same. In any experiment, it's really important to control all variables and only change one. So if we are trying to run an experiment to see how concentration affects the rate of the reaction, but at the same time we're also changing the temperature, then it's really difficult to attribute what the change in rate is to. So rate laws keep everything constant, and then we just vary the concentration generally of the reactants. Rate laws have to be determined experimentally. In other words, there's no way that you can just look at a chemical reaction and somehow figure out what the rate of that reaction is going to be. You have to roll up your sleeves, get in the lab, and run the experiments. So what you're going to get is data collected from these rate law experiments or these kinetic experiments, and you're going to go ahead and see if you can really kind of make sense of the data. So let's look at a really simplified reaction here. We've got A plus B yields Z. So in this case, A and B are our reactants. Z is our product. So if I was going to write a rate law expression for this reaction, I would write rate, so the speed of the reaction, is equal to K, which is some constant, times the concentration of A to the N, times B to the M. So let's break this down in a little bit more detail. K is our rate constant, and K is going to be different for every reaction. It's one of those non-constant constants, which I know sounds a bit like an oxymoron, but if you think about the last unit, we talked about the freezing point depression constant and boiling point elevation constant for water, and how if you're looking at a different solvent, you get different numbers. It's the same thing here. If you look at a different reaction, you're going to get a different rate constant. Those square brackets around A and B are two reactants. That's representing the concentration of those two species in terms of molarity. So we talked about molarity in the previous unit. That's moles over liter. So we're going to be varying the concentrations over the course of the reaction and kind of seeing how the rate of the reaction responds to it. M and N are what are called the orders of the reaction. And this is where, in my opinion anyway, like 90% of the thinking when it comes to solving rate law problems takes place. We're going to have to look at data and see what values M and N should have. And for our purposes, they're always going to be whole numbers. We're going to keep it as straightforward as we can in this lesson. But the larger the values of M and N, the greater changing that reactant, or changing the concentration of that reactant, the larger the impact that has on the speed of the reaction. So if you're a little bit confused right now, don't panic. That's pretty normal. This is really abstract until we actually start looking at real numbers. So determining the order, so solving for M and N, again, that's pretty much the most difficult part of this whole process. So let's talk a little bit more about that. If you change the concentration and nothing happens to the rate, so for example, I double the concentration and the rate does not change at all, what would the order be? Or just kind of instinctually, if you had to assign a number to this process where you make a change and the reaction doesn't change the speed at all, what number would you probably assign? And no change, I would be thinking 0. This is what we call zero order in terms of that reactant. So I changed the concentration and it seemed to have 0 impact on the rate. If you change the concentration and the reaction rate changes by the same amount, So you increase the concentration of one of the reactants by twice as much, so you've doubled its concentration, and now the rate doubles. Well, it's kind of the mirror image of each other, so we call this first order. Let's say you change the concentration and the rate increases by a factor of x squared. So you triple the concentration and the rate increases by 3 squared, or 9. Is this exponent of 2? We call this second order. And again, this is probably not making a ton of sense at this exact moment in time. Don't panic. Once we start applying it, I promise it makes a whole lot more sense. But just be comfortable with these 3. In reality, these are not always going to be whole numbers. They can actually be negative numbers as well. You can have what are called inhibitors. But for our purposes, we're going to stick to this. If we change the concentration and there is no effect on the rate, we call that 0 order. Change the concentration and the rate changes by the same amount, first order. And if you change the concentration and the rate increases by a factor of x squared, we call that second order. And these are the 3 orders that we're going to be using most frequently at this point in time. When we're working with rate laws, there are really 3 different questions that can be asked. The first can be essentially asking, what is the order of the reaction according to each reactant? So in the previous example, how do we solve for the values of m and n, the orders? I can ask you to solve for the value of K. What's the rate constant for that reaction under those conditions? And I can ask you to try to figure out what the rate will be if the reactant concentration changes. So we're going to tackle these 3 different types of problems today. And we're going to be using this reaction. F2 plus 2ClO yields 2FClO, all gases. And in your workbook, you have this data table. So we've gone through and we've run the same exact reaction. Looks like 3 different times for 3 different experiments. And what we've done is vary the concentration of our reactants. We've changed the amount of F2 and ClO. And then we've watched what has happened to the rates. So these are all in molars, our concentrations, both of the F2 and the ClO. And our rate is always going to be a concentration per unit time, usually molarity per second or molarity per minute. And we can see that as we change the concentrations, the rate changes. So let's spend a little bit more time trying to figure out the order of the reaction according to each reactant. Our general rate expression is going to look like this, our rate law expression. Very generically, we've got rate is equal to K times the concentration of one reactant raised to the power times the concentration of the other reactant raised to a power. And you can imagine if I had a third reactant, I could just make, that third term like this. And what we're trying to figure out is what should the numbers or the values be for N and M. And in order to do that, if we want to find the order of F2, we need to find 2 experiments where the concentration of F2 changes and the concentration of ClO is constant. So let's see if we can find 2 experiments that kind of fit that description. Okay, so if I look at experiments 1 and 2, I see that the concentration of F2 has changed. Or I guess I could look at 2 and 3 potentially. And over here, I want the concentration of ClO to stay the same. So it's definitely going to be experiments 1 and 2. So what we do is we take a look and see what has happened to the concentration of F2. So it went from 0.1 molar up to 0.2 molar. So in other words, it doubled. So any change in the rate can be attributed to this change in concentration of F2. So let's take a look at the rate. The rate went from 0.0012 molar per second up to 0.0048 molar per second. So it looks like I doubled the concentration and the rate went up by a factor of 4. So it went from 2 times to 4. So 2 to the what would give me 4. So I would say that'd be 2 to the second is going to be equal to 4. Since this is raised to the second power, I know that N, the order of the reaction according to F2, is going to be 2. So I'd say this reaction is second order in terms of F2. Let's try to repeat this for ClO. Find 2 experiments where the concentration of ClO changes and the concentration of F2 remains the same. Let me get some of this stuff out of the way. If we look at experiments 1 and 3, F2 stays constant at 0.1 molar. ClO goes from 0.1 all the way up to 0.01 up to 0.04 molar. So I quadruple my concentration of ClO. I'm going to take a look at what happens to the rate. It goes from 0.0012 up to 0.0048. So it too has quadrupled. So if when I change the concentration, the rate changes by the same exact amount, I know that is first order. So I would say that this reaction is second order in terms of the concentration of F2 and first order in terms of the concentration of ClO. If asked for the overall order of the reaction, it's as simple as adding up those exponents. So 2 plus 1 gives me 3. Overall, this is third order. So I'd say my rate law looks like this. Rate is equal to K times F2 squared times ClO. And if you want to go ahead and write the 1 in there, you can, but it's not necessary, it's implied. All right. I think this is the hardest part, or at least the part that requires the most thought in the whole rate law problems that I can ask you. So let's move on and take a look at another problem. In this case, we want to try to solve for the value of K. Now we know that the rate law looks like this. Well, let's see. You want to solve for K. You have information about the rate. You have information about the concentration of F2. And you have information about the concentration of ClO. You can pretty much just plug and chug. Just make sure that you're using the same experiments. It doesn't matter whether you choose experiment 1, 2, or 3 in this case, but you can't take like the initial concentration of F2 from experiment 1, the initial concentration of ClO from experiment 2, and then the initial rate of the reaction from experiment 3. You have to be consistent. So if you plug everything in, I've decided to use experiment 1, but again, it really doesn't matter. And you can write molar in here with the M if you want to, but it's implied with those square brackets. That means concentration and molarity in chemistry. And you come up with K is equal to 12. Hopefully from a mathematical perspective, getting the number 12 is not too tall of an order. Coming up with your units for K can be a little bit more difficult. The units for K change. If we think about it, we have rate in molar per second is equal to K, which is some constant. And in this case, we have the molarity of F2 squared times just molarity. So for those of you who don't like units, trying to figure out the units of this is going to be difficult because it does require you to do some thinking. For those of you who are really conscientious with your units, this probably won't be so bad. So I need to find a way to end up with just molars per second when I multiply my units for K times m squared times m. So I kind of have this, km cubed, and I need to get that to molar per second. So if I divide both sides, how do they teach it to you? I guess we go 1 over m cubed, multiply by 1 over m cubed. That's going to get rid of the molar up here. That's going to turn this into molar squared. I have K is equal to 1 over molar square seconds. And another way to represent that is with this -2 and -1 exponents. This definitely requires a little bit more thought, and you kind of have to work through your units. So be careful with that. It just takes some practice. All right. Last but not least, I can ask you once you've found the constant, the rate constant, to figure out what the rate would be with different concentrations. So let's say that we run experiment number 4, and we've got F2 at a concentration of 0.3 molar and ClO at a concentration of 0.03 molar. Can you predict the rate? You sure can. You know that rate is equal to K times concentration of F2 squared times the concentration of ClO. Start plugging in what you know. The rate constant is going to remain a constant. Once you figured it out for one of the experiments, it's going to be the same for all of them. So it's 12. I've given you new concentrations to plug in. No big deal there. So you can solve for the rate. In this case, you get 0.0324 molar per second. And the units for rate are always provided in the question. Okay, this is tough stuff. Let's go through and look at a practice problem together and make sure that we've got this. Okay, let's see, went through that. Okay, let's take a look at question number 4. Is this still recording? There we go. Yes, it is. Okay, so question number 4 gives us a really generic reaction. A plus B yields C. We want to find what the rate law is. Okay, so we know that rate is always equal to K times the concentration of one reactant to some power. I'm just going to leave that blank for right now, times the concentration of the other reactant to some power. If I want to find how the rate of the reaction is affected by changing the concentration of reactant A, I need to find an experiment or 2 experiments where B remains constant and A changes. So let's see if we can find 2 that work out. I'm looking at experiments 2 and 3. The concentration of B stays exactly the same, and it looks like the concentration of A doubles. So if I look at experiments 1 and 3, what's happened to the to the rates? It looks like the rate has quadrupled. So I doubled it, and the rate changed by a factor of 4. That sounds like we're describing a second-order relationship. Let's do the same thing for reactant B. I need to find 2 cases, 2 experiments where the concentration of A remains the same and the concentration of B changes. I can look at 1 and 2, or I could look at 3 and 4. In both cases, the concentration of A stays constant and the concentration of B is doubling. So as I double the concentration of B, if I look at my 2 rates, that comes pretty close to doubling as well. It's not a perfect double, but that's okay. That's pretty darn close. So if I double the concentration of a reactant and the rate changes by the exact same amount, that's describing a first-order reaction. And that's pretty much it. From there, it's about plugging in, using your calculator, and playing around with the units. So I really recommend doing some practice with this. This can be very, very challenging, especially if it's new to you, and I'm guessing for most people this is brand new. It takes a little bit of figuring out and puzzle solving to find the orders of the reactants, but once you've got those, it's plug and chug. Alright guys, thanks for tuning in, and I hope you found this lesson helpful.